All right, my friends. So this is my first attempt at trying to give lecture virtually via any kind of recording or anything like that. When last we left off, we got about halfway through my lecture videos, or not lecture videos, handwritten lecture notes. And basically I want to just pick up where we left off, and I'm going to continue on as if you were sitting in front of me listening to, taking my lecture. So this format is going to be a little interesting, and you're going to have to bear with my handwriting. I'm going to do my best. But writing on a tablet is not something they teach you in school, so I'm working on it. So last thing that we did was we talked about calculating energy of transitions for electrons, right? So we talked about energy of transition for an n equals 2 to an n equals 4 and that sort of thing. We talked about excitation and about emission. So the last thing that I want to talk about with that is the subject of ionization energy. And you'll have to also bear with me. I'm left-handed, and occasionally my hand will cause things to happen unintentionally on the screen. But ionization energy essentially is, we're talking about what the energy it takes to remove an electron entirely. Not just move it from one spot to another, but take it off of the atom entirely. So for our purposes here, let's talk about if I have n equals 1, and if I'm going to remove an electron, that means that I'm essentially going to n equals infinity. Okay? So this is my initial state, and here's my final state. Right? So I'm taking an electron from n equals 1, and I'm taking it off entirely. So it's going to be, you can think of it being infinitely far from the nucleus. Okay? So I can use that same equation, that Rydberg equation. I can say delta E, wait, I don't want to be in red. I can say delta E equals R sub H, and it was initial squared, 1 squared minus 1 over infinity squared, right? So this was initial, and this is final. Now, that guy is effectively 0. Right? Because infinity being the largest, it's infinite. So 1 over infinity, 1 over an infinitely large number, basically makes that particular character 0, right? So, and then 1 over 1 squared is basically just RH, right? It's R sub H, which equals 2.179 times 10 to the minus 18 joules. Right? So this matches experimental data really well. Right? So we can look at a hydrogen atom, atom of hydrogen gas, and we can ionize it and make it H plus gas. Okay, and this is an ionization equation. All right, so I can calculate this for an electron starting in any level. I could say, what is it to ionize an electron if it starts in n equals 2, n equals 4, n equals 5, any of those things. And I can just figure out whatever 1 over that squared is times R sub h. Okay? So ionization is the energy it takes to remove an electron entirely from an atom, right? And that pretty much does it for what we can do with the Bohr model, okay? Because the Bohr model only works for 1 electron species, 1 electron atoms. Okay, so things like hydrogen, lithium 2+, helium+, stuff like that. So anything more than that, we're in trouble. Doesn't explain multi-electron atoms. Multi-electron species, which is pretty much everybody, okay? So, enter quantum theory. And we sort of already talked about quantum theory with Max Planck and all that sort of thing, in that electrons can only make, stepwise jumps and, quantized energy. No halfway measures, everything's one step at a time. So quantum theory, there are the 2 main ideas in quantum theory. One is the whole idea of wave-particle duality. That's not how you spell particle. Particle duality. And 2, the other thing is a thing called the uncertainty principle. Okay? So the first idea is that everything, idea 1, is that absolutely everything has wave-particle duality. That means electrons, it means dust particles, it means a football, it means you, it means me, anything like that. The trick is that the smaller the particle, the more the wave-like behavior becomes important. Stop. Wave-like behavior is important. Okay? And I'll do a little demonstration here, a little math demonstration here in a second. But the person that we can thank for sort of demonstrating this is I believe he was a French scientist, I may be wrong about that, named de Broglie. Okay, and he did his work, he was most notable in 1924, all right? Gave us a wonderful equation. Lambda equals Planck's constant divided by momentum, so mass times velocity. Okay? That's Planck's constant, mass, velocity, and this thing is called the de Broglie wavelength. Okay? So let's think about something that is sort of macro, okay? So let's talk about a large object. Something like me, for example, as a human being. All right. So let's say that I am moving. Let's say I'm moving at 2 meters per second. And my mass is 76 kilograms. Okay? So let's see what my wavelength is. Okay, so if everything has wave-particle duality, obviously I am a solid object, so I have that particle part. But what is my wavelength? Let's take a look. So I plug in my numbers. So 6.626 times 10 to the minus 34. Now, Planck's constant is in joules seconds, but remember joules can also be written in terms of kilograms, meters, and seconds. So kilograms times meters squared over seconds squared times seconds, because that's joules seconds, divided by 76 kilograms times 2 meters per second. Okay, and let's put this in terms of nanometers. So let's say, let me see where to write it, times 10 to the 9 nanometers in 1 meter. Okay, and so what we get is my wavelength for a macro object like me comes out to be 4 times 10 to the minus 27 nanometers. Okay. Let me put that into perspective. Not really in perspective, but let me just explain that this is incomprehensibly small. Okay. Talking about wavelengths, so visible light is somewhere above 400 nanometers, right? And my wavelength is 4 times 10 to the minus 27, okay? It really doesn't even come on the scale, all right? But let's think about what it would be for an electron traveling at 0.1 of the speed of light. Okay, so 1/10 of the speed of light. So lambda here equals 6.626 times 10 to the minus 34 kilograms meters squared over seconds squared times seconds. And an electron is 9.109 times 10 to the minus 31 kilograms, so it's very, very small, and it's traveling very, very fast, 0.3 times 10 to the 8th meters per second, right? And we say convert to nanometers times 10 to the 9 nanometers in 1 meter, right? So the wavelength of an electron traveling at 1/10 of the speed of light comes out to be 0.0242 nanometers, right? That's X-rays. Okay, so the smaller the particle and the faster it's going, the more important its wave behavior becomes. All right. So now, I'm not going to get into the uncertainty principle. We can. It's actually, they're really kind of fun problems. But our textbook doesn't really dig into it very much. I have plenty of notes on how to do the problems, but we're not going to for the sake of just getting through this material. But the uncertainty principle, I will tell you what it is. Okay, so the uncertainty principle is stated as this. So basically, let me do it basically. We cannot know, and I think we talked about this in class a little bit. I think I had to have a little stop talking moment because of stuff. But basically, we cannot know the exact position and momentum of an object at the same time. Okay? The important part about that is not only the and, but this bit, the exact part. Okay? So there's an equation for it which says that the uncertainty in position times the uncertainty in momentum is greater than or equal to Planck's constant over 4 pi. Okay? Now we can go through and we could talk about, the difference between the uncertainty in a macro object like me versus a micro object like, or a subatomic particle like an electron. And that's where things actually start to become important, kind of like with the de Broglie wavelength thing. When you get down to subatomic particles like electrons, the uncertainty in position and velocity actually become important. Okay? So, but we're not going to get into the math of that because we don't need to. Okay, so if you're following along with my lecture notes, handwritten lecture notes, there's a whole bunch of that stuff about that, because it is kind of fun to talk about. So, but suffice to say that along with all of this, we can move on to start talking about locating an electron and how we go about finding one. Okay, so what they did right around the time of de Broglie and Max Planck and all those guys was they started to try to figure out how they could do this mathematically. Okay, so to locate an electron, they already figured out that things were behaving like waves, so we model it with a standing wave. Okay, and the easiest way to do that is with a thing called a particle in a box. Okay, so let's imagine that we have a box with a length L. Okay, and flying around in that box, we have one particle in one dimension, and it's going to go let me try again. I want it to go right there and right there. Okay. There we go. All right. So right here, that's 0. Okay. So anything above or below that line, you're likely to find a particle. Okay. But at these places where it crosses 0, that is referred to as a node. Okay? So a place where at a node you have no chance of finding a particle. Okay? So there's a rule that says basically for any given quanta, the number of nodes equals n minus 1. Okay? So in this case, for this particular situation, I have the number of nodes is 2. So if 2 is my number of nodes, then n must equal 3. Okay? Now, we will talk a little bit more here about how to and what all that means here in just a second. All right. But suffice to say that if I have n equals 3, then my nodes equals 2. If n equals 5, my nodes equals 4. Okay? Because the nodes equals n minus 1. Right now, what we do is we take this and I use a thing called psi. Okay? And psi is what we call a wave function, a wave equation that describes a matter wave. Okay? And to do that, I'd say psi is a function of x equals the square root of 2 over the length of my box times sine times my value of n times pi times my location in the box divided by the length of the box. Okay? Let me reiterate something, or make something very clear. You don't need to know this. Okay? This is demonstration. This is describing to you how we get to a lot of this information. Okay? So, to find my location in the box, I use this wave equation with psi, okay? And the reason for that is that L is analogous to the distance from the nucleus. For an electron. If my particle is an electron, L is basically the size of my atom, and then I can use the equation of psi to figure out where my electron is. Okay? So, but what they do is since the uncertainty principle says that I can't know the location and the momentum at the same time, what I do is I generate a probability. Okay? So I say psi squared, okay, equals 2 over L sine squared of n pi x over L. Okay? And what that does is it takes me from this, which is my wave, right? And when I generate my probability distribution, which is what this is, probability distribution. Okay, so that's what I get when I square psi. All right, and what that does is it tells me no chance of finding an electron there. Okay, because that's at a node. Okay, so this is why we care about the nodes, because the nodes tell us where we're not going to find electrons. Okay? And what it does is what it does tell me is that I'm probably going to find most of my electrons here and here. Okay? At a certain distance from the nucleus. Okay? This is why we care. Right? Now there's some really lovely and quite hideous equations that I could put you through, and one of which is the Schrodinger equation, but we're not going to need that either, so we're going to cut that out. All right, so all of this is a big preamble to get into quantum numbers. Okay, so there are 4 quantum numbers, right? First of which is called the principal quantum number. The principal number, okay? That's n, right? And n can be 1, 2, 3, etc. Okay? And what it does is it tells us the shell number. Okay? And I'll explain this in what it means to be a shell number here in a minute. Our next number is called the angular momentum number. Okay? And the angular momentum number tells us the orbital shape. Okay, what shape is the orbital? And it has the symbol L, okay, a little cursive L. And L can be 0, 1, 2, 3, etc., as long as it is n minus 1. Okay, that is super important. Okay, L can never be the same as n. Okay, make this very clear. N can never equal L. Okay, so what this tells us is the subshell number. Okay, so if I have, so it tells us my shape, my orbital shape. So if L equals 0, we refer to that as an s orbital. Okay. If L equals 1, we call that a p orbital. If L equals 2, we call that a d orbital. If L equals 3, we call that an f orbital. Okay? And theoretically, this keeps going up. Okay? But what we have on the periodic table only goes up to F, right? But they theorize that it could go higher. Okay? So our next, I told you there were 4 numbers, so that's the first 2. So our next number is the magnetic quantum number, and we call that m sub L. Okay? And m sub L can be minus L to positive L, including 0. Okay? And the magnetic number tells us the orientation of an orbital, which direction it's pointing. Okay? So, for example, if L equals 1, then m sub L can be negative 1, 0, or 1. Okay? So anything from negative L to positive L, including 0. Right? And lastly, we have the spin quantum number. Right? And this is for telling us electron spin. Okay? And this one's the easiest one of all. called m sub s for spin, and it can only be one of two things. It could be plus a half or minus a half. Okay? So let's think about, let's sort of put this into perspective. Okay? So for s orbitals, right? If it's an s orbital, L has to be 0. And since m sub L can only be negative L to positive L, if L is 0, that means that m sub L can only be 0, right? And the idea is that we have one s orbital per subshell. Okay. So p orbitals, right? If you're a p orbital, your L value equals 1. And m sub L can be anything from minus L to positive L, so minus 1, 0, and 1. So that means that we have 3 p orbitals per subshell, right? That means 1, 2, 3. Okay? Let's come down a little bit. All right, if you're a d orbital, then L equals 2, and m sub L minus 2, minus 1, 0, 1, or 2. All right? So that means there are 5 d orbitals per subshell. Right? Just like before, I've got 1, 2, 3, 4, 5. Right? And just to be complete, let's talk about F's. Right? So if we're an F orbital, L equals 3, m sub L minus 3, minus 2, minus 1, 0, 1, 2, or 3. So that means there are 7 F orbitals per subshell. Okay? All right. So, one important piece of information, giving a star. So we get a max of 2 electrons per orbital. Okay? And the other important one is that the max value of L is n minus 1. Right? So each orbital, so if I say that I've got 5 orbitals for 5 d orbitals, each one of those d orbitals can hold a maximum of 2 electrons. So if I fill up all my d orbitals, that means that 10 electrons can go there. Does that make sense? I don't know why I'm saying that as if you're sitting there able to respond to me, but that's the deal. So let's sort of talk about this. So, no, I don't want to be red. Let's switch to green. Let's be Christmassy. So if my n value is 3, and let's say my L is 0, or 1, or 2, as long as it's not 3. Okay? So if my n value is 3, the most my L value could be is 2. Okay? So that means that I've got at L equals 0, that's an s orbital, right? So I've got 1 orbital there, right? Then I've got, if my L value is 1, then it's a p orbital. and I've got 3 orbitals there. If my L value is 2, then that's a d orbital, 3d. There's 1, 2, 3, 4, 5 there. Okay. If my n is 2, then I can have my 2s, and I can have my 2p. Okay? Because if my L value is 0, then that means an s orbital. If my L value is 1, that means a p orbital. Okay? But if my n is 2, then I can't get an L value of 2. The best I can do is an L value of 1. Okay? If I have an n of 1, all I've got is my 1s. Okay? Because I can't get an L value of 1. Because n, or L, can always has to be n minus 1. Okay? There's more crazy business. All right. So, with all of this business, with all of this good stuff, one more very important thing. No 2 electrons can have exactly the same 4 quantum numbers. The quantum numbers are kind of like an address, okay? And what this is called the Pauli exclusion principle. Okay? All right. So, let's talk about quantum numbers and orbitals. And we're going to do this in blue. All right. So, if n equals 1, how many nodes do I have? Zero, right? Because my number of nodes is n minus 1, right? So if my n is 1, then that means that my L equals 0, which means an s orbital, right? So if I have no nodes, what that means is that I have a sphere. Whoops. Sphere with no nodes. Okay. If my L value is 0, then that means that my m sub L equals 0. Because there's no spatial orientation for a sphere. Right? And my m sub s can be plus a half or minus a half. Okay? Because there's a maximum 2 electrons per orbital. Okay? So I could say 1 electron, if I'm dealing with this scenario. Stop. So my quantum numbers are arranged like this. N, L, m sub L, m sub s. Okay? So for an electron in this scenario, I could say 1, 0, 0, plus a half, or 1, 0, 0, minus a half. Notice these are not exactly the same four numbers. They differ in the plus a half or minus a half. Okay? So you can have 3 out of the 4 numbers being the same, but the whole set has to be unique for each electron. All right? Now, if we are dealing with, let's change up to black. So if n equals 2, that means that I have 1 node, right? So then L can be 0 or 1, okay? So 0 is an s orbital and 1 is a p orbital, right? So if it's the s, then m sub L equals 0, and that makes this a 2s orbital, right? So it's still a sphere, so I've got my sphere, but I also still have the 1s in there, okay? The 1s makes a node. We call this a radial node. On the inside. Okay. Now thinking about P though, right? So M sub L will be -1, 0, or 1. Okay? So we can think about this because the M sub L is an orientation thing. Let's think in 3 dimensions. So this can be a 2p in the y direction, a 2p in the x direction, or a 2p in the z direction. Okay? Now I don't want you to get hung up on which number is which. Okay? Just know that these are set up in 3 dimensions, right? We're starting to talk about more than just 1D particle in a box. So the way this works is we have the equation for this guy gives us a probability density that looks like this. And let's say this we're talking about the 2px. Okay. All right. So what we get is an angular node. Okay? Or we call it, or it can be referred to as a plane. All right? So with the value of 2 for n, right? If n equals 2, then that means that we have 1 node. If it's a p orbital, that node is an angular node. That's a plane. If it's an s orbital, then that means that we have that 1s making a radial node on the inside. Okay? Angular nodes versus radial nodes. All right? So another little trick, because the maximum value of the max value of L is n minus 1, that means that it also tells you the number of nodes. The L value does. Okay? A little bit of a trick there. Not trick, but you know. All right. So for the next thing, like if I continue on, I'm not going to try and draw all of these orbitals, because after the p orbital, like the d orbitals start to get crazy, the f orbitals get even worse. So I'm going to refer you to your textbook. Let me see if I can find them. All right, so your textbook has some images, orbital shapes, on page 234 and 235. Right, and it doesn't even bother trying to show the F orbitals, but you can Google that business because they get a little crazy. All right. So let's think about this. So if we have, so we've done n equals 2. So if n equals 3, that means that we have 2 nodes, right? And the L value will be 0, 1, or 2. That maximum thing says that we get 2 nodes, right? The max value of L, right? We get an M sub L of -2, -1, 0, 1, or 2. Okay? Because that 2 is a d orbital. Right? So M sub L is the orbital orientation, so that means that I get 5 orbital orientations. Or 5 orbitals entirely. Okay? And I'm not going to try and draw this business. All right. So hopefully this makes a little bit of sense. So if I were to draw, or sort of give you a set of quantum numbers, stab. Let's say I said 3, 1, 0, and plus a half. Okay. Is it valid? Is it a valid set of quantum numbers? And the answer is yes, because the L value, let's see, remember N, L, M sub L, and M sub S. Right? The L value does not exceed the N value. The M sub L value doesn't exceed L. Okay? So this is good, right? What if I said 2, 2, 1, and minus a half? Is it valid? No. N cannot equal L. Okay? If I had 3, 2, 3, and minus a half, is it valid? No, because that one cannot exceed L. Okay? So you need to be able to determine whether or not you have a valid set of quantum numbers. All right. Right, now, it is getting late, and I think that I may stop there. Or maybe not. Never mind. Because I can do electron configurations with my eyes closed, because that's our next thing. All right. Electron configurations. Okay. Now, for the most part, doing electron configurations is as easy as reading a book, right? Reading top to bottom and left to right. Now, I invite you at this point to go get a periodic table. Stab. Okay, I'm not going to try and paste one in real time. or any of that business. But you should have one nearby. There's a great one in your textbook. All right. But I'm going to draw one, a bad one, to be sure. Okay, which is not too bad. Right, so what I want to illustrate is that on the side of the left-hand side of your periodic table are these numbers. 3, 4, and actually, 5, 6, and 7. Okay, and we want this to come down further. There we go. Okay. So those on the side there, surprise, surprise, that is your n value. Okay? So all those numbers on the left-hand side of the table, that is your value for the principal quantum number n. Okay? Now, the periodic table is broken up into sections. We're going to do S, and in the middle here are D's, and let's do P's are over here. Okay, and then the F's are the lanthanides and actinides. Okay, so the only weird one, is helium. Okay, helium here is really 1s2, right? And I always forget whether these are supposed to be superscripts or subscripts. That should be a superscript, not to get you mixed up. Okay, so if I start, so in order to figure out like what the electron configuration of something is I start at the top left and I read across left to right, top to bottom. Okay, and what I do is I list things as they become full. Okay, so up here, let me zoom in some. All right, so up here, let's use some green. So this is 1s1. This and then helium over here, 1s2. Right? I'm reading left to right, top to bottom. So in my next row, here's 2s1, 2s2. Okay? And then if I come over here, now I'm in the P's, 2p1, 2p2, all the way over to 2p6. Okay? And so on and so forth. And then, so as I fill something, that means filling is 2s2 or 2p6. Okay? When I fill an S block or fill a D block or fill a P block, that's when I list it. Okay? Now, electron configurations are a lot like an element's address. Like its street address. Okay? So let's just do, the easiest way to deal with this is to just do a couple. Okay? So if I want the electron configuration for, let's say, lithium. Okay? So I'm going to start and list everything that gets full. Okay, so I'm going to start. This is where you want to be looking at a periodic table with me. Okay, so looking at helium is top of the table on the left. So helium is 1s1, or excuse me, hydrogen. Sorry, hydrogen 1s1, and then helium is 1s2. When I get to the 1s2, that is when I list it. Okay, and then lithium is in the next row, and I list where it is. So that is sitting at 2s2. 1s1. Okay? So you can think of, in terms, like in keeping with this street address analogy, you can think of the 1s2 is kind of like the street, and the 2s1 is like the house number. Okay? All right? So let's do a couple more. Let's talk about, let's say, carbon. All right, I'm going to start at the top. I'm going to list everything that is full. So helium's 1s1, hydrogen is 1s1, helium is 1s2. So when I get the S, all I can fit are 2 electrons in an S. I list it. So 2s2. 1s2. Boy, I'm getting all confused. Okay? Then, now the 1s is full, so now I go to the 2 row, and I get lithium's 2s1, beryllium is 2s2. That means that that is full. And then I continue across. Now I go straight all the way across. I don't try to dip down into the transition metals. I just go straight across to boron. Right? And boron is at 2p1, and carbon is at 2p2. Okay? So that 1s2, 2s2, that's like the street name, and then carbon's address on that street, its house number, is the 2p2. Okay? Because I'm in row 2, and I'm in the second column of the p block. All right? Let's try fluorine. Okay? So 1s2 gets full at helium. And then I go lithium, beryllium. That puts me at 2s2. That gets full. Now I cross over and I get to the p block. And I go boron's 2p1, carbon's p2, nitrogen's p3, oxygen's p4, fluorine is p5. So row 2, fifth one in the p block. Okay? Let's do silicon. All right, so we get 1s2, 2s2, 2p6. I'm just reading left to right all the way across, right? And then I get to row 3, sodium's 3s1, magnesium's 3s2. And then I continue across and I get aluminum's 3p1, silicon is 3p2. Right? Row 3, second column of the p block. Right? Now, you can imagine as we go along, this gets worse and worse and worse, and these get longer and longer and longer the farther down the table we go. So we have a thing called the noble gas notation. Okay? So what I can do is this piece is the electron configuration for neon. All right? And the way I usually write this is I'll put it in a bracket. Okay? So if I use the noble gas notation, what I do is I find the noble gas above it, then just list everything in its row. Okay? So for silicon, my noble gas above it is neon, and I put it in a bracket. And then I just list everything in neon's row, or excuse me, silicon's row. Okay? So it's like shorthand. Right? So if I wanted to do magnesium, I find the noble gas above it, which again is neon, and just say 3s2. And that's it. Okay? Now, when dealing with things that are in row 4 and below, the D block goes back a number. All right? So, for example, if I wanted to talk about titanium, okay, I'm going to use the noble gas notation, and I'm going to say the noble gas above it is argon. And then titanium's row starts at 4s, and that is calcium is 4s2. And then titanium, when I hit the D block, I have to drop down to a principal number of 3. So then it becomes 3d2. Okay? I'm still just reading left to right, but when I hit the D block, I have to drop down a number. Okay? Now, when I get out of the D block, I go back up. So past the D block, go back up. Okay, so if I wanted to talk about, for example, germanium, right? Still using the noble gas configuration, I say argon, I say 4s2, and then the D's are 10 across, so 3d10, and then when I get to gallium, when I get just past the D block, I go back up to 4 and say 4p2. Okay? And this is how it goes, right? It's always just reading left to right, top to bottom. You can use the noble gas configuration. You just find the noble gas above it and list that, and then list everything in its row, right? Now, there are exceptions, all right? There's a couple that have weird noble gas weird electron configurations, right? And those are chromium, copper, molybdenum, and silver. Right? So let's talk about chromium. Chromium's a good example, right? If I were to do, as I've been instructing you so far, if I write the electron configuration for chromium, I would say argon, and I would say 4s2, 3d4. Okay? Now there's a little problem, because if I take this and I break it into like boxes, let's say I make a box for each orbital. 3, 4, 5. Okay? So these are my d orbitals. Right? And I put an electron in each one, 2, 3, 4. Okay? Completely half full is very stable. Okay, right now I'm missing an electron from getting to a half full set of Ds. So what it does is we borrow from the S. Right? So it's going to take one of my S electrons and plunk it in there. Okay? So what I get is that chromium, its electron configuration is actually 4s1, 3d5. because my s electron loaned, or my s orbital loaned an electron to the d block, or to the d orbital. Okay? Because 5 electrons in d is more stable than 4. Okay? So the same thing happens with copper. Right? Right, this is the correct. Right? So if I do the same thing for copper, we would assume 4s2, 3d9. Right? And if I have my d orbitals 3, 4, 5, and I put my electrons in them, completely full is very stable. Okay, so it does the same thing. Okay, so copper has the correct electron configuration 4s1, 3d10. Okay, the same thing happens with molybdenum because it's at a d4, and the same thing happens with silver because it's at d9. Okay. You may wonder about tungsten, seaborgium, gold, and I'm not sure what Rg is. These don't do this. Okay? Because there's hinky stuff that happens with their, because there's F electrons involved in those guys, so they don't need to borrow the same way. Okay? But the important exceptions are copper, chromium, molybdenum, copper, and silver. Okay, those are important exceptions. All right, what do we have left to talk about? I think not much. This is a long video. Okay, so let's talk about filling. Okay, let's change colors because I'm getting bored here. Filling orbitals. Okay, so we fill orbitals like I've been talking about. We start at the top left and we read left to right, and that's how we fill our orbitals. So if I have a 1s, then I'll have a 2s, and then it'll go to 2p, right? So if I have, let's say, carbon, I'm going to put one electron at a time, and they're going to be opposite spins, right? So, because the Pauli exclusion principle says that no two electrons can have the same 4 quantum numbers. So, I've got to have a plus a half and a minus a half. One to spin up, one to spin down, okay? One spin up, spin down, and then we have spin up, spin up. What I won't do is load them together. Okay? They will fill each orbital individually before they start to pair. Right? Let's see, what else do we have? We've got those exceptions, and I think that does it for my handwritten notes. Okay, so the last thing that I want to talk about really quick is a concept called isoelectronic species. Okay, So iso means same. Okay? So the idea here is that we're talking about different species that have the same electron configurations. And this can happen because of ions. Okay? So let's think about something like, let's talk about oxygen. Okay, so its electron configuration would be helium, the noble gas above it, and then 2s2, 2p4, right? Now what about O2 minus? Okay, if I'm 2 minus, then that means 2 more electrons, right? So if I write the electron configuration for O2 minus, 2p6, right? Now, what is the electron configuration for neon? Right? If I were to write the electron configuration for neon, and use the noble gas above it, which is helium, and I say 2s2, 2p6. Okay? These guys are the same. Okay? I can do the same thing with, let's say, magnesium 2+. Right? So if I take, well, let's start with just magnesium. Okay? Magnesium is neon 3s2, right? If I make it magnesium 2+, then it's just neon, right? Which is the same thing as saying helium 2s2, 2p6. Okay? So if they have the same electron configurations, if we're a negative ion, we add electrons. If we're a positive ion, we take them away. We can have different species that are isoelectronic. So we would say that magnesium 2+, neon, and oxygen 2- are all isoelectronic. Okay? Or we can call it an isoelectronic series. All right? Whew. So that was me writing like 18 pages of notes. I hope this was helpful. We will have a test on Friday. You have, I don't know why I'm doing this, going all the way back to the beginning. But you have a test on Friday. Your assignment for Chapter 6 is due, I think, Thursday. So good luck, Godspeed, and I'll be in touch.